All right, what I'm going to do is I'm going to work through a couple of these problems here for you. And I'm going to start here with number 11 on multiple choice. It says a glass containing an ice cube is filled to the brim and the cube floats on the surface when the ice cube melts. Well, I'm going to tell you that let's talk about what happens. So before we give you any type of answer to this, let's talk about what happens here. Okay, so as we look at this, we find out that, or we know that ice has a lower density than water. Thus, right now the ice is it has a greater volume. The ice has a greater volume than what it would be if it was water. So what that means is when it melts, all right, when the ice melts back into water, it's going to go back to its natural volume, or what its volume would be when it's water, and it's going to be less than what it was as ice. So thus, the water level will go down. So our correct answer is right here, B, the water level decreases. So let's look at number 12. Comparing an object's average density, P naught, to that of a fluid, PF, the density of the fluid. What is the condition of the object to float? So what I'm going to do here is just take a look at a simple example. It says similar to ice and water. Ice has a density of 0.9 grams per cubic centimeter, and water is 1 gram per cubic, and that should be centimeter. Ice floats. So what do we know? We know that the object has to have a lower density. So the object's density has to be lower than the fluid's density if you want something to float. And that's why ice floats, because when it freezes, it becomes bigger or gains volume, which means its density goes down, and that's why it's able to float in water. Okay, ocean-going ships in port are loaded to what's called the plimsoll. This right here should be in the plimsoll mark, and which is a line indicating the maximum safe, that should be the maximum safe loading depth. However, in New Orleans, located at the mouth of the Mississippi River, where the water is brackish, which means it's partly salty and partly fresh, ships are loaded until the plimsoll mark is somewhat below the waterline. Why? Well, let's talk about what's happening. So they're ocean-going ships, meaning they're going from fresh water into the ocean. And what we know then is that salt water has a higher density. Thus, the boat's going to float at a higher level in the water. As the density of whatever fluid you're trying to float in becomes higher, it takes less of that object to be submerged in water to create a buoyancy force equal to enough to keep that boat afloat or object afloat. This means that there's going to be more mass added to the boat to take it back down to the plimsoll mark. And right now it's in brackish water. Well, what's going to happen to the density as we get full-fledged out into the ocean? That density is going to even increase more. So that's why they take it to a mark that's slightly below, or slightly sink it down to a mark that's slightly above the plimsoll mark. All right, because as they go out to the ocean, it's going to gain density, which means it's going to make it float at a higher level. Hey, so let's talk about this one. A heavy object is dropped into a lake as it descends from the surface. Does the pressure on it increase? Does the buoyant force on the object increase? Well, I'm going to actually address this one here. Does the buoyant force on the object increase? Remember, the buoyant force is equal to the weight of the displaced fluid, or in this case, the weight of the displaced water. And the water, the density of water is not going to change, and the volume is not going to change. So the buoyant force on it is actually going to be the same. So let's talk about the first part here, the pressure on it. Well, pressure increases, and our equation for pressure is pressure equals force over area. The area is going to remain constant, but the weight of the water pushing down increases with increased depth. And what I mean by that is weight, or the force, is mass times gravity. Mass is volume times depth, and volume can be broken down into length times width times height. Well, it's this height that matters here. As it goes down, the height of the water that's above it, the height is increasing. So the water that's above it has more volume, which means if it's going to have more volume, then as V gets bigger, it's going to have more mass. As mass gets bigger, it's going to have more weight pushing down it, or more force. So that means the force is going to get larger. So the pressure will also increase. Okay, so let me tell you what this comes down to. What we're really going to do here is compare the volumes of what it is and what it should be. All right, meaning if it's all gold, it should have a certain volume, and if it's not gold, then what is the volume? So we're going to compare what the volume of, find out what the volume of this object would be if it was gold, and then find out what the volume of this object must be, and compare the two. So what I'm going to do here first is we have some given information. All right, we know that the density of water is 1,000 kilograms per meter cubed, and the density of gold is 19,300 kilograms per meter cubed. So I did some simple math and said, okay, if the density of gold is 19,300 and the mass of this crown is 0.8, and if it's all gold, then the volume of it should be 0.000414 kilograms per meter cubed. So that should be the volume of this when we're done, if it's entirely gold. So let's find out what we get. So what I'd start off here with then is said that when we put it in water, all right, the apparent weight or the apparent force is equal to its actual weight minus the buoyant force, how much is pushing up on it. So if I break it down to its equations, the apparent weight of the object is equal to mass times gravity minus the buoyant force is the density of water times the volume of the object times gravity, because the buoyant force is equal to the weight of the water, and the weight of the water is the volume of the water, or the volume of the object, times the density of water if that object was full of water, times gravity. Well, from here then, we're just going to simply solve for V naught. And what I've done is the apparent weight, they tell us, is 7.3. The actual weight is its mass times gravity. The density of water is 1,000. Gravity is 9.8. Let's solve for the actual volume of the object. And this crown had an actual volume of 0.0053 cubic meters. That means it can't be gold. All right, it can't be gold because its volume was supposed to be 0.00414. All right, so here's our last problem we're going to go over. So the steel cube, 0.3 meters on each side, is suspended from a scale and immersed in water. What will the scale read? Well, what we get here then is, what we want to find here is the apparent weight. All right, that's what the scale is going to read, because again, we have the real weight minus the buoyant force is going to give us the apparent weight, or what the scale is going to read. Some things that we know is the density of water is still 1,000 kilograms per meter cubed, and the density of steel is 7,900 kilograms per meter cubed. And this one I just looked online and found. So all we're going to do here then is we're going to find the actual weight. That's going to go here for the steel. We're then going to find the buoyant force. Well, we have to find out what the volume of this is, and they tell us it's a cube, and each side is 0.3, so we're going to find the volume. And then we're going to take it times the density of water times gravity. And that's what's going to go in for the buoyant force. When you subtract the two is what you're going to get for the apparent weight. Well, the volume of these two then is length times width times height, or 0.3 cubed, which is 0.027 meters cubed. And then the rest of this becomes pretty apparent. The mass is the density of steel times the volume. Well, the density is 7,900. The volume is 0.027. Turns out to be 213.3 kilograms. That's the mass of the steel. So let's find the weight of the steel, because that's what we got to do here, is the weight of the steel. And that's 2,090 newtons. So that goes in here for the weight. The density of water. Now we're going to find out what the buoyant force is. So now I've gotten rid of the buoyant force and put it in its equation, which is the density of the water times the volume of the object times gravity. So when we do that, I haven't typed that one in yet. Let's go ahead and type that in here. The apparent force, or what the scale is going to actually end up reading, is going to be 1,825 newtons. So that's what we're looking for there. Well, hey, hopefully that was beneficial for you guys. I'll catch you on the flip side.